don't know what Penrose diagram is? Okay, most people know Penrose diagrams are. Okay, I have some other questions that I'll ask later. Also, you should tell me, of course, if it's going slowly or too fast or whatever. I'm happy to adjust it. Okay, so the most basic diagnostic of thermalization is to take a system which is near equilibrium and then perturb it by a very small amount to see how it relaxes back to equilibrium. So we can diagnose that by looking at a two-part function. The expectation value of the thermal state of these operators, or phi is some operator in the theory. In general, we could have different operators here, but I'm going to take the case where they're the same operator. So here we're writing this as an expectation value in the thermal state, but sometimes it's convenient. This is an expectation value in a mixed state, have an expectation value in a pure state. And it's not, for some reason it's not as widely understood as it should be, that the thermal field theory and thermal states and quantum mechanics are not necessarily mixed. I mean, the essential features of thermal states are that we're talking about relatively high energy states in the spectrum of energy states where we have an extensive amount of energy in the system. It's not so important that it's a mixed state. So, for example, we get almost the same answer if we take the expectation value and a pure state beta, which I'll define in a moment, of 5G50. And here, beta can be under suitable conditions, it can be basically any state with the right energy statistics. So in particular, we would like to have that the expectation value of the Hamiltonian in the state beta should be equal to the thermal expectation values. Okay. And actually, it's important that we would like higher moments to agree as well. The idea that these things should be basically the same is part of the story called the eigenstate thermalization hypothesis. Okay, this is not like Penrose diagrams, so maybe I'll say a couple of words about that. So this is an idea. It's roughly what I said. The idea is that, actually, the more precise version of the idea is that if we look at energy eigenstates of a interacting system, of a suitably interacting system, then those energy eigenstates will locally look indistinguishable from a thermal state. In particular, if we take an energy eigenstate E, and we form the rank 1 density matrix out of this thing, and we trace it over the complement to compute the thermal density matrix of subsystem A in an energy eigenstate. The claim of the eigenstate thermalization hypothesis is that this density matrix will very closely approximate the trace over A complement of the thermal density matrix, provided again that we take the right energy here. Okay, does this make sense? Are you guys familiar with this idea of tracing over part of the system and getting a density matrix on the rest of the system? So we're going to show hands about whether you're comfortable with that. Okay, somewhat comfortable, somewhat uncomfortable. So here what I mean is we imagine that the system is an extended system of many sites. Okay? And we could consider one of two types of states here. We could have the thermal density matrix from the full system, or we could have this energy eigenstate. And then if we look at the density matrix on a subsystem A, the claim of the eigenstate thermalization hypothesis is that that density matrix, rho A, which is equal to this object, will be approximately equal to the same density matrix that we would compute in the thermal state. Okay. This was sort of an elaborate slide. Yeah. So here what I meant by writing beta was just a pure state with, let's say, the expectation value of the energy that agrees with the thermal expectation value of the energy at inverse temperature beta. So that's what beta means. Actually, it doesn't need to be an eigenstate Hamiltonian. The important thing is that it should have almost all states with the right expectation value of the energy will have this property. Yeah, this is I think, an underappreciated fact. That talking about thermal states of systems, you don't really have to drag around the thermal density matrix. You can talk about pure states. You just have to talk about relatively high energy pure states. Okay. Yeah, okay. So the squiggly is hiding a lot. Yeah, so let's discuss that a little bit. Part of the motivation for this eigenstate thermalization hypothesis comes from thinking about random states. So, for example, if we take a random state in Hilbert space here, and then we look at a subsystem, then the density matrix on that subsystem will be the same as the maximum mixed density matrix, which would be, in this case, the partial trace of the thermal density matrix, up to exponentially small corrections in the degree to which the subsystem we're looking at is smaller than half. So that's what this squiggly means in that case. But actually, for real systems, it's not as simple. Because for real systems, let's say we take an energy eigenstate here. The statistics of the energy here will not be exactly the same as in the thermal density matrix. In particular, in the thermal state, there's some slop in the here will have power law corrections in the size of A divided by the total system size. So in either case, if we're looking at small subsystems of a very large system, this will be very close to an equal sign. But whether it's exponentially close or power law close depends on, well, it's power law close for what I wrote here. Okay, so the point of this is that it's nice now to be able to think about the two-point function as an inner product of two states, one where we acted phi at 0 on the thermal state, and one where we acted phi at t on the thermal state. Okay, what we would like to see as a probe of thermalization is that this quantity should go to 0 at large t. So let's just work out